Hello, we are going to discuss now a mathematical model that incorporates vaccination. Perhaps this is the simplest way of addressing vaccination for an epidemic model. So we are going to refer to the basic model that has three compartments known as susceptible, infected, and record, the SIR model. First, to refresh our memory, we're going to review some of the equations that do not incorporate vaccination. And then in this process, we are going to note that this is an SIR model for vital. This is what we call vital dynamics. And what we mean by vital dynamics is that there are some terms here, like this term, that denotes demographic processes. And those processes, demographic processes, are denoting natural, well, it has to be birth due to natural causes, right? So these are newborns. And here, this term denotes the new arrivals into the population are all assumed to be in the compartment denoted by S, which is what we call the healthy individuals that are not carrying the pathogen. These are called the susceptible individuals. But also we have terms that are subtracting out of every equation. We have minus mu S, then we have minus mu I, and then minus mu R. These terms denote when individuals are dying. Individuals are dying here at a constant rate, a rate that is equal to all compartments. And this is death due to natural causes. So this is like natural death. Okay. So this process, this model incorporates birth and death of individuals, and therefore we call this vital dynamics. The other thing to remember is that the total population here is denoted by N. N is the sum of S plus I plus R. Here we have state variables S of t, I of t, R of t, right? So there is a vector with state variables, and the parameters, there is mu, there is beta, and there is gamma, right? So this model has three parameters, and it also has three state variables. So let me make room here. Okay, I'll make room because I want to summarize everything I just told you with a diagram. Okay, so we have the compartment we call S for susceptible. We have a compartment we denote with I for infected or infectious. And then when individuals, their immune system fights off the infection, they develop immunity and they are no longer capable of passing on the pathogen. So they go into this compartment that we denote with the letter R. Okay, so we have some arrivals and departures out of the total population. Everybody that arrives is assumed to arrive into the S compartment, to the susceptible compartment. And then we have departures out of each compartment. So these are the terms of the so-called vital dynamics, right? The newborns are assumed to be susceptible, and then at a constant rate, the same constant, there are individuals that are dying out of every compartment. And the mathematics in this model works in such a way that we can easily verify that the total population is constant. But the important things, the important events for the epidemic process that is being represented or approximated here with these equations, the important events are infection, when an infection takes place, and that happens at a rate that is equal to beta times S times I divided by N. So this is the rate at which individuals move from the compartment of susceptibles into the compartment of the infected. And the other event is the recovery, the rate at which individuals move out of the infected compartment into the R compartment, right? And that happens at a constant rate, gamma. So the rate of recovery here, the individuals are transferring from I into R at a rate I times gamma. That was for the model without vaccination. If we would like to revise the equations so that we incorporate vaccination, there is a very simple approach to do that. The approach being the following, that we are going to remember. Previously, we had parameters. We had the parameters beta, gamma, and mu. Okay, beta is the transmission rate, the rate at which infection is transmitted from one host to another host. Gamma is the constant rate of recovery, and mu is the rate of death, but this is death due to causes, natural causes, right? It's not necessarily due to the infection. So now with this model, what we're going to do is we are going to incorporate an additional parameter called P. P, in fact, here is going to be a parameter that is assumed to be between 0 and 1. Okay, and what this parameter is doing is that P denotes, here we're going to say that P denotes coverage. Okay, this is the vaccination coverage. So we can think of this as the level, the fraction or the proportion in the population of individuals that are immunized, that are vaccinated. Okay, so one simple way, you could write down equations very similar to these equations and have an additional compartment in which individuals that are immunized are housed. But an approach that's even simpler than writing a separate compartment is to think of those, remember the newborns? Previously, we were assuming that all newborns were arriving as susceptible individuals. And so what we could do here when we have this fraction of vaccination coverage is that we can basically split the arrivals and say a fraction P of those arrivals are going to be assumed. We're going to assume that they are immunized. Okay, so this is, bear with me, this is just an introduction of a model. This is a very crude approximation of keeping a separate account, or accounting for the individuals that are immunized in the population. But basically what we're doing here is that we're splitting that amount mu times n of new arrivals, and we're going to say, we're going to send a fraction of those, we're going to assume that are immunized, and 1 minus p is the fraction that is not immunized, is the fraction that is not protected by the vaccine. So we're going to assume that now there's a fraction 1 minus p of the arrivals of the newborns that is entirely susceptible. Okay, so the equations are going to look very similar as before. You see all the previous elements, right? We have departures from every compartment, that stays the same. The transition from S into I is happening at the same rate, beta Si over n. The transition from I into R also happens at the same rate, gamma I. So all those parts or expressions of the mathematical model are going to stay the same. But then the compartment R here has a new arrow, right? Has some new term. It has gamma I was there before, mu R was there before, but this will be a new term, a new expression to account for in the mathematical model. So here we have the equations. We can see that the differences is what we were pointing out. The equation for the susceptible compartment now has that extra term 1 minus p times mu times n, and the other terms are the same terms we had before without vaccination. And the other new part is that we now have a fraction. We have a fraction here. This actually should read, this here should read p times mu times n plus gamma times I minus mu r. Okay, so we have a fraction p times mu times n that now is representing individuals that are from the start of this process are assumed to be immunized. Okay, and there is another typo here. You're going to bear with me. So the total population is still n equals s plus I plus r. Okay, so because n is the sum of the total population, then it's easy to verify that the derivative of n equals 0. So let's verify that. So we have, this is a verification. We have that n equals s plus I plus r. So what happens if we take the derivative in both sides? We differentiate with respect to t. Here we differentiate with respect to t every term. And if we do this, if we take the derivative with respect to t, then we find that I'm gonna go back to the equations. I'm gonna write the equations there for you. So so what we find is the derivative of s is 1 minus p times mu times n minus beta s times I over n minus mu s. Derivative of I is beta s I over n minus gamma I minus mu I, and the derivative of r is p mu n plus gamma I minus mu r, right? So this equals the sum of the derivatives, and so there are terms here that you can see this term cancels with that term, the gamma I cancels with this term, and it seems that this is turning into, we can add here mu n factor 1 minus p plus p, and then we have minus mu times s plus I plus r. And so it's simple, it's easy here to conclude that, right, so this term is gonna become, this is gonna become 1. So we have mu times n, and s plus I plus r is n. So we have mu n minus mu n, which is 0. So what we have verified there is precisely that the derivative of n of t equals 0, and this implies that n is a constant. Okay, n is a constant because its derivative is 0. So the total population is constant. Because the total population is constant, then remember, we were assuming that n is s plus I plus r. So what we can do is divide by that constant in both sides of that equation, and that gives us that 1 equals s divided by n plus I divided by n plus r divided by n. Each of these quantities is now a proportion, is a fraction. So we're gonna rename these fractions. Basically it's like introducing names for new variables. We're gonna say the fraction of the susceptibles. When you take the number of susceptibles and scale that by the total population size, then that now becomes a proportion or a fraction, and we're gonna call the fraction x, okay? So now remember, s is a function of time, n is constant, and because s is a function of time, you're dividing by a constant, then what you're saying here is that this is x of t. X of t is s of t divided by n. So if you are interested on taking the derivative of x, then you will find that that means that you're taking the derivative of s of t divided by n. N is a constant, and this becomes the derivative of s with respect to t multiplied by the constant 1 over n. So let's actually carry out this calculation. So that means that we have the following. We have here 1 over n multiplying, I'm pretty sure I can write this so that it fits. This will multiply 1 minus p times mu n minus beta s I over n minus mu s. Okay, so that expression, I'm going to continue this calculation here. That expression is becoming 1 minus p times mu minus beta s over n I over n minus mu s over n. So what happens when 1 over n is distributed here, multiplied by each of those terms? In the first multiplication, you have n divided by n, that disappears, okay? And this is now taking this form, okay? Remember, this is the derivative of x with respect to t, okay? That is the derivative of x with respect to t. So suppose that we call y, x is s divided by n. Suppose that y is I divided by n. Okay, suppose that y is I divided by n. So that means that we can make this expression, we can write this expression as 1 minus p times mu minus beta x times y minus mu x. So what we are saying is that the derivative of x with respect to t is now written as constant 1 minus p, quantity 1 minus p times mu minus beta times x times y minus x. Okay? So this is what we are assuming before, right? So now let's assume that y is I divided by n. That means that when we compute the derivative of y with respect to t, we're multiplying the derivative of I times the constant 1 over n. Okay, so let's see what this looks like. This is 1 over n times, the expression we have here is beta si over n minus gamma plus mu times I. Right, so we're gonna distribute this quantity 1 over n times that term, 1 over n times that term, right? So this becomes beta s over n times I over n minus gamma plus mu times I divided by n. So remember that x is s divided by n, so we can write this as beta xy minus gamma plus mu times y, and this will be the derivative of y with respect to t. Okay, so this process of dividing by a constant or multiplying by a constant is what typically in mathematics is called rescaling, because you're bringing quantities to a new scale. And now we can basically do the same thing for the last state variable, z, defined as r of t divided by n, and the derivative of z becomes the derivative of r scaled by multiplying times a constant 1 over n. Right, so this is even simpler than the other expressions. This is 1 over n multiplied by p mu n minus p mu n plus gamma r, plus gamma I minus mu r. Okay, so that means that this is p mu plus gamma times I over n minus mu times r over n. So we can write this as p mu plus gamma times y minus mu times z. And remember, this is the derivative of z with respect to t. Okay, so we have rescaled the system by multiplying by a constant. This constant is 1 over the size of the total population. So the model with the SIR model with vaccination, rescaling by the constant population size, now looks in this form. So now we're calling the state variables x of t, y of t, z of t, right? It's still a vector with 3 variables, but now these variables are proportions. So at every time point, when we add up x of t plus y of t plus z of t, then that summation adds up to 1, right? They are fractions or proportions. The parameters are still the same parameters we had in the original model. So we have p, beta, gamma, and mu. Now we have 4 parameters, right? P denoting the coverage of vaccination in the population. Now, one thing to observe here is that from this model, we have that y1 equals x plus y plus z. This implies that you could solve for one of these variables in terms of the other variables. So if I solve for z, for example, I can have that z equals 1 minus x minus y. So in the 3 equations that I have here, wherever the state variable z appears, I could substitute z by 1 minus x minus y. However, we should notice that z only appears on the last equation, okay? Z only appears on the last equation. On the first 2 equations, there is no z. But if there was an expression with z, we could do that substitution, okay? So basically, because z only appears on the last equation, z as a state variable is redundant. And because it's redundant, that means that we can actually do without that state variable. So we can simply work with the 2 equations that involve state variables x and y, okay? And so this is now what we would call a reduced version, reduce and rescale model, right? Is a reduced version of the SIR model. X and y denote fractions, okay? So we're gonna do something else with, we're gonna do something else here with this. Actually, we're gonna take a short break and we will come back for part 2, which has to do with getting rid of dimensions.